say I want to thank Nancy for that very generous introduction. If I was only 5% of what she described as me, yeah, I'd be very happy. I know I'm not. So today, I want to talk about machine design innovation. And I'm hoping that by the time my talk is over, I will have convinced at least some of you to take engineering as a, maybe not as a profession, but at least as a hobby, or pursue it in your leisure time. So I want to talk about, thank you, how technology and education has the potential to transform the machine design paradigm. Now, technology, and to some extent education, is already changing how we do prototyping, how we do rapid manufacturing. And you guys have probably heard about 3D printers, using which you can convert your ideas into physical products that you can sell in the marketplaces and actually have a sort of a boutique business of yours. But what I'm going to argue today is that it is not sufficient to just have rapid prototyping or democratization of the manufacturing process, which is what 3D printers and service bureaus where you can send your design to print are enabling. It's equally important that we have design tools, because you can't print what you can't design. You need to have the design tools that can help you actually do the design. And since I'm a machine designer, my focus is more going to be on the machine design aspect of things. People are saying that we are already living in a third industrial revolution. So when we say third industrial revolution, which means there must have been two before, first one is well known to us, right? It started with James Hargreaves, the guy who invented the spinning jenny a long time ago, about 250 years ago in Lancashire in Great Britain. And that spawned a whole industry of cotton mills. Second industrial revolution is considered to be the time, and historians could debate about that, somewhere between 1850 to the end of the First World War, when the steam engine was invented, the locomotion was invented, and of course Henry Ford, to whom we credit mass production and customization. So if we are living in this third industrial revolution era, to truly realize the benefits and fruits of this third industrial revolution, we need to have the tools that will make our life simpler in terms of designing machines. So what I'm going to do in today's talk is I'm going to present to you actually a tool that we have recently developed that will allow machine designers to actually generate the mechanism design concepts. And that's the hardest part of doing the machine design. That's an early stage process which requires an art and science together, which can generate the mechanism design concepts that can make the main motion of the machines possible. So I'm going to talk about that, and I'm going to talk about how education can actually change how we do the machine design. So before we talk about the machine design process, I want to get some terminology out of the way. Okay, we often hear about the terms like invention and innovation. What's the difference? Well, if invention is the spark of an idea that has to be nurtured, has to be provided the oxygen, then the fire that follows after that spark is innovation. To give you a simple example, Edison invented the light bulb. That's an invention. All the light bulbs that came after that, CFL, LED bulbs, and now we're talking about the smart bulbs that are connected in your home, are innovation on that invention. On the other hand, when Apple invented the iPod, sometime in around 2005, that was not an invention. It was an innovation on some of the existing MP3 players. What Apple did was created a great ecosystem that could tie into the iTunes, as well as they created a great, beautiful product, which was very easy to use. And then the entrepreneurs come in, and of course, they catch the fire, and they try to monetize it the way they can. And then they try to watch for the next spark and the next big fire, and that's how they make money. Let's talk about machines and mechanisms. And this is going to be sort of an introduction, because I don't want to assume that everybody knows what a machine is or what the mechanisms are. So machines are devices that allow you to basically transmit and transform forces and motion from one form to another. They can consume energy, they can produce energy. Your car is a great example of a machine. Now, that machine has a lot of mechanisms. One of the primary mechanisms that you have in there is that you have this sliding or a reciprocating motion of the piston that has to be converted into a rotary motion so that it could be connected to the wheels of your car, and your car would go. If you ever open the hood of your car, you'll find lots of mechanisms inside it. You will see a timing belt that runs around the pulley. You'll find the gears if you look underneath. So these are all different examples of the mechanisms. So machines typically have lots of mechanisms in them. And the mechanisms are responsible for imparting a specific motion to the machines. Okay, so that's a very simple example, and you have lots of mechanisms in the machine. Another example, what you're seeing over here, is what is known as a linkage mechanism. So on the left-hand side, you're seeing basically a spider bot. It's a robot that basically works based on a linkage system given rise to by CLAN, and so it's called CLAN linkage. It's a 6-link mechanism. And you can see they're numbered from 1 to 6. It's a 6-link mechanism, and the idea is that when you put it together in a certain way, which requires a little bit of creativity, you can actually make a spider walk. And this is a robot that can possibly walk. So my talk is mostly going to be focused on linkage systems as mechanisms, not on the gears, not on the cam systems or the pulleys and things like that. I want to give you a few more examples of the machines. And I'm going to pick the examples from rehabilitation and physical therapy area. So what you're seeing on the left-hand side are exoskeletons. And exoskeletons are actually not available. It's not like you can go to Walmart and buy one, right? I mean, they cost upward of $100,000. They're still in research, so technology-wise, they're still in infancy. Of course, some soldiers are actually experimenting on them, and some have been produced and used by some soldiers. But they, on the cost and technology spectrum, are at one end. On the other hand, you have very simple devices, which some people may actually even refuse to call machine, but I would still call them machine because they have, if you look at the walker, they have little wheels underneath, and that's a basic machine. So you have simple devices like walker, you have the wheelchairs, which could be manual, could be automatic, and they're on the other end of the cost and technology spectrum. You could get a walker at Walmart for $25. Manual wheelchairs are slightly more expensive, but they're still much cheaper compared to the exoskeleton. So if you look at this cost technology spectrum, you have the products at two ends. But there is nothing in between. And the question I had was, why don't we have products in between? Now, it's not like that you don't have products in the middle. You do have some products, but it's a very, very narrow range. And the products have no variability, really. No customization. It's like one size fits all kind of devices. So we have developed a couple of prototypes that you're seeing over here, and one of them I'm going to talk about and show you actually at the end of my talk. This is a mobility assistant that we designed and developed for a retired doctor, and I'll have more to say about that. And what this does is it basically helps a disabled individual to get up from a seated position. And once the person is up, the same person could actually use it as a walker. So it's a multifunctional mobility assist device. Now, we have licensed the technology behind the device to a local company called TEDx Medical Systems, and by 2015, we should have a product in the market. So they're going to bring the product out in the market, so you might actually get to see it. So I'll have more to say about that a little bit later. But this particular product is somewhere in between, I say. This is going to be priced at about $3,500. So it's somewhere in the middle of the cost and technology spectrum, and it's a very different kind of product that you will find, because there's nothing like this in the market, although there are other products that try to mimic this functionality. So the next question is, what's our motivation for doing this kind of work? Okay? And motivation exists at multiple levels. So as an educator, I always worry about how are we going to train our students to become the engineer of 21st century. So they are prepared to do great engineering, to design things that can transform people's life, that can change the society. And it's well accepted by everybody that we need to introduce design challenges, design problems, design projects early in a student's education. So when they come in to our department, we want to expose them to design problems. And they may not know all the theory behind designing linkages or the machines and things like that. That's okay. We are at that stage of the technology where we can actually teach them programming. We can teach them electronics. And they will be able to design the machines. And I've seen that happening firsthand for the last 3 years. So that's something we need to do. National Academy of Engineers, they produced a report called Engineers of 2020 where they said that passive lecture-based instruction should be replaced with active learning. And it should incorporate modern engineering tools, the design challenges, and things like that. So that's what we want to do. That's our motivation. And what you're seeing at the bottom are the 3 pictures of the robots that actually students in my Mech 101, it's an introductory level mechanical engineering class, have designed and built, and they work. Another motivation for this actually comes from outside the classroom. So if you've been following the technology a little bit, you're aware of 3D printers, right, from MakerBot. You're aware of shapeways.com, a company where you can actually send your designs and they'll print it for you if you don't have a 3D printer and send it back to you. Or you can rent the tools at tech shops or MIT hobby shops, and there are 8 of them in the country today. where you can go and 3D print things, you can CNC cut, you can do laser cut, you can use a sewing machine, they have soldering station, they have CAD workstation, you can use any of those tools and actually turn your idea into a physical product. And that is democratization of manufacturing. This is giving rise to a subculture called DIY or do it with others, which is feeding into this movement called maker movement or maker renaissance. Somebody has called it renaissance of novices, because you don't have to have an engineering training, a professional degree to actually do this kind of stuff anymore. And this is, again, following on the democratization of some other technologies that have existed before. When the personal computers came around, when the printers came around, it democratized the computing and publishing for the people. Nowadays, you have electronics prototyping platform like Arduino and Raspberry Pi, which are very easy to program. There was a time when people had to use assembly language programming to actually program them. Not anymore. You can use vanilla C++ programming. So object-oriented technology democratized the programming. Programming used to be hard once upon a time until procedural-oriented programming came, and then object-oriented technology came around. Then the next thing is, what do you do with the products that you actually design and build? You can ask for funding at Kickstarter or some other platforms. Or you have marketplaces like Etsy, where you can actually put your creation for sale yourself. And here's an example of the sort of product that you might see on Etsy.com. So this is a docking station, and it's a working docking station, created from the driftwood that these people who created this device collect from the seashore of Maine. And that's phenomenal. It costs $120. You're not going to find this in Walmart, but it's a great product. If you have money to burn, sure, why not? Get it and put it in your living room. Look nice. What is going to tie maker movement and the crowdfunding platforms like Kickstarter? Well, you have to have a glue that's going to bring them together. Like I said before, you can't print what you can design. Where are the design tools that will make the design possible? Well, you do have some design tools. You have Google SketchUp, which is a very easy-to-use CAD software. Housewives can use it. You have 3D CAD. You have online CAD softwares. Autodesk, which is a powerhouse in CAD softwares, has come out with a tool which you can download on your iPhone, on your iPad, and actually design the shapes. And that's all great. You can do this shape design. There are quite a few tools out there. But as a machine designer, I always ask, where are the tools that will help people design the machines? Because if we want to go past printing the keychains on your 3D printer or just the case of your iPhone or your Android phone, then we got to have tools which are serious but are fun to use. We need the tools. So from these two motivations came two outcomes. One was this class that I designed called Freshman Design Innovation, and one of the SUNY grants actually supported this. And in this class, basically, I tried to teach the engineering principles, mechanical engineering, electronics, programming, everything in a design context, where the students, their ultimate project is to create a device, create a robot that's autonomous in nature, has sensor controlled, and can actually execute useful or entertaining motions. And what you're seeing over here is basically a 4-bar linkage on the left-hand side. You have 4 links over there. That's the simplest possible linkage you can put together that makes the walk of a robot possible. The second outcome was an app, and we're developing it for Android as well, but right now it's ready for the iOS, called MotionGen, that allows you to basically create mechanism design concepts for a given motion. So you give a motion, it can give you basically different types and topologies of the mechanisms that can execute that motion. And this is a very important tool, because this is a tool that allows you to do the true synthesis, and there's no tool out there in the world today which actually allows you to do true synthesis. Most of them are simulation tools. It also allows you to do reverse engineer the mechanism. So if you have a pattern and you want to get around it, you can actually design alternative mechanisms that will allow you to avoid the patent infringements. So I want to show you a demo of the app that we have actually developed. Right? So this is how the interface actually looks like. So one thing we can do is we can quickly sketch mechanisms. We can say, this is the point that I'm interested in, and I can hit the play button. That's a very nice tune. Thank you. So you can see how the mechanism is actually moving. And now if I want to design a robot that walks, I can change some of the parameters and see how my linkage is actually going to generate newer paths. And of course, you have to have some idea where to go and what direction you need to go. But you're getting there. And that's your linkage for designing a walking robot, because if you look at the trajectory of the foot point, it follows a squished D or a bean kind of path. Not only that, what we can do is we can actually take, let's say, a picture from textbook, and this is a picture, and I have it in my photo library. I could take a picture, there's a camera functionality here as well, and what I can do is I can actually sketch right on top of it. I can sketch right on top of it and see what the motion would be. And you can see it's now on the other circuit. I'm going to change it so that I can see what it looks like. And this is a mechanism for transporting, for moving a film of a motion camera. And now what you can see is that, yes, we can not only generate the path, and let me darken it, and you can see how close it is. You can interactively change some of these parameters and see how that path changes. So now you can actually experiment. You can take a static picture from a textbook and turn it into a live mechanism right away. And you can play with any parameters and see how that path changes. And that's great, but that's not the true strength of this app. The true strength of this app is in doing the true synthesis. So one way we can do that is by specifying a motion. And 5 happens to be a magic number in kinematics community, where we can specify a motion by specifying a few poses. So that will be position and orientation in the space. In this case, it's just a planar thing. And I've got a mechanism that actually goes through those 5 poses. It's going to interpolate through the positions as well as orientation. Another example I want to show you is the motion of a shoulder joint as somebody gets up. So this will be the basis for our sit-to-stand device that I'm going to demonstrate pretty soon. So I have 5 positions over here, and as soon as I enter them, the app computes what the linkage is going to look like. And while I'm demonstrating them, this particular thing, I'm going to ask my students to come and actually attach themselves to the device so that they can show you how it's actually going to work. So this is the sort of path that the shoulder joint follows when you actually get up. So this is the device that I want to talk about, but it's actually not about the device. This is about a retired doctor for whom we designed this. Now, the device we have created, we have licensed the technology, and that's a success story, but I'll tell you the truth, it's a failure. It's a failure because we couldn't actually design this device and deliver it to him in time so that he could use it. His condition has deteriorated to the point that he can no longer use this device. It took us many years to design and build this. So it's a failure in that regard, but because of him, now we have a device that potentially could be used by hundreds and thousands of people, maybe by next year, if not millions, and help them actually. So this is a device where what we are trying to do is we are trying to mimic the natural trajectories of the joints when you get up. Okay? So this one tries to follow the trajectory of the shoulder joint. So Subrat is going to show you how the linkage system works. So this is a 6-bar linkage system you have seen, and he's going to lift himself up, and he doesn't have to exert any of his own load. He's going to get up. And then once he is up, he can lock his knees. That's a prerequisite. He can begin to walk. He can just push the device around, and he can begin to walk. And if he gets tired of walking, he could just sit in the sling because his center of gravity is always falling within the footprint of the device. He's not going to fall. And once he's done with his job, he can have eye-level conversation. He can go make his coffee in the kitchen. He can go back, position himself next to the chair, and lower himself down. So what have we learned from this? Well, if we have the right design tools, we have the sensors which are cheaply available, the programming is easier, prototyping is easy, which means that any of us can be an inventor or innovator if we have an idea what we want to do. And one area that could especially benefit from this is the assistive device market, because the assistive device market is highly customized. Every individual has a different kind of disability. Companies are not going to make products for one individual because there's no money to be made if it is a small market. But if people had the access to the design tools like these, then they could actually design devices like this and actually print themselves or get them manufactured from a service bureau and put them together. So I want to end my talk by acknowledging a few people, and there are quite a few because this is not the stuff that I've done all by myself. There are many graduate students, many undergraduate students, my collaborators, Jeff and Patricia Aceves, and they're great guys to work with. But most importantly, Dr. Pillai. I wish that he would watch this sometime. And if there are any applause at the end of this talk, they should be all reserved for him. Thank you.